Hello, everyone, and welcome to Bookercast, the podcast where books come to life.
And I'm so excited to dive into another amazing story with all of you.
Whether you're a bookworm or just love a good story, this is the place for you.
Every episode, we explore incredible books, talk about their stories and characters, and share insights that'll make you fall in love with reading all over again.
All right, let's not keep you waiting any longer. Get comfortable, and let's jump right into it.
Sounds good.
All right, buckle up, everybody, because we're about to dive into some really deep waters today. We're talking about Sean Carroll's Something Deeply Hidden.
Yes. A book that really tries to unpack, the many worlds interpretation of quantum mechanics.
And it gets pretty wild, right? I mean, we're talking about the nature of reality itself.
It does. It definitely does. But what I appreciate about Carroll's approach is that, he doesn't get lost in the weeds of complex equations.
Yeah, he really emphasizes that it's about understanding the concepts. Like, he uses that analogy of throwing a rock, remember?
Oh, yeah, right. He compares it to Newton and classical mechanics.
Right.
When you throw a rock, you can predict where it will land, right? Clear cause and effect.
Exactly. But then you enter the quantum world and things get a lot weirder. It's like there's this gap between what we see and what might actually be real.
Exactly. Like, we can't pinpoint exactly where that quantum rock is going to land. It's almost like the universe is playing dice with reality, right?
And that makes a lot of physicists uncomfortable. It's almost like they don't want to accept the implications of their own theories.
Yeah, well, that's what makes it so interesting to explore. So how did we even get to this point, right? Like, how did we go from thinking about atoms as these tiny solid particles to this whole quantum mess?
Okay, so let's back up a bit. How did quantum mechanics even come about?
Well, like most scientific revolutions, it started with scientists realizing that their old models just weren't cutting it anymore. We used to think of atoms as the smallest, most fundamental building blocks of matter. Like tiny billiard ball.
Indivisible.
Right, exactly. But then, boom, we discovered electrons.
And everything changed.
Pretty much. Suddenly, the atom wasn't so simple anymore. It had this internal structure. And to explain how electrons behaved, we had to introduce this concept of fields.
Fields, okay. So how are those different from particles?
Well, think of a magnetic field. It's not a bunch of individual particles, right? It's this continuous force that exists everywhere in space. That's a field. And in quantum mechanics, fields are fundamental.
Got it. But where does light fit into all of this? Because we normally think of light as a wave.
Right. But here's where things start to get really weird. Light, even though we think of it as a wave, can also act like a particle.
It can be both.
Yep. Einstein called these particles photons. And that was a huge deal because it basically showed that the distinction between particles and waves is kind of blurry in the quantum world.
Mind-bending, for sure.
It is. And it gets even weirder because it turns out that particles, like electrons, can also exhibit wave-like properties.
Wait, what? Seriously?
Oh, yeah. And this led to this whole idea of the wave function, which is this mathematical description that tries to capture the wave-particle duality of everything. It's like the core concept of quantum mechanics.
So everything is described by this wave function. But is it like a real thing? Or is it just a mathematical tool? How do we know it's not just, our limited way of trying to make sense of the universe?
That's where this really famous experiment comes in. The double-slit experiment. It's basically the experiment that blew everyone's minds and showed that quantum mechanics was the real deal.
Okay, tell me more about that.
So imagine you have a barrier with two slits in it, and you start shooting electrons at it one by one. If electrons were just particles, you'd expect them to go through one slit or the other and hit the screen behind it in two distinct bands.
Yeah, that makes sense. Two slits, two bands of electrons.
Right, but that's not what happens. Instead, what you get is an interference pattern like you'd see with waves.
Hold on, you're saying that individual electrons are interfering with themselves?
Pretty much. It's like each electron is going through both slits at the same time, even though it hits the screen as a single particle. It's like it's interfering with itself.
Whoa. Okay, that's already hard to wrap my head around.
I know, right? But it gets even weirder, because if you try to observe which slit the electron goes through, the interference pattern disappears. It's like the act of measuring forces the electron to choose one path or the other.
So by simply observing, we change the outcome of the experiment.
Exactly. It's like our consciousness is somehow entangled with the experiment.
Okay, this is where my brain starts to melt a little bit.
Yeah, well, you're not alone. This is known as the measurement problem in quantum mechanics, and it's a problem that has led to all sorts of different interpretations of what's really going on.
And one of those interpretations is the many worlds interpretation, right?
Yeah.
Which is what Carroll is arguing for.
Precisely. It's the idea that every time a quantum measurement is made, every possible outcome actually occurs, but in different universes. So in the double slit experiment, there's one universe where the electron goes through the left slit and another universe where it goes through the right slit, and so on.
So every time we make a decision, every time a quantum event happens, the universe splits. That's a lot of universes.
It is. But it's also a very elegant way of interpreting the math. And that's what Carroll argues for. He says that the many worlds interpretation is the simplest and most straightforward way to understand what the equations are telling us.
So we're basically living in a multiverse. It's a lot to process, a lot to process.
Definitely.
I think we need to unpack this many worlds idea a bit more, but maybe we should take a pause here, come back to it after a break.
Yeah, let's give everyone a minute to catch their breath. There's a lot more to explore in the quantum realm. Welcome back, folks. Now, before the break, we were knee-deep in this idea of a constantly branching universe where every quantum measurement creates new worlds.
Yeah, it's a wild concept. I'm still trying to wrap my head around it, to be honest.
It takes some getting used to, that's for sure.
Definitely.
But, before we get even deeper into that, I'm still kind of hung up on this whole idea of entanglement.
Oh, yeah. Entanglement. Spooky action at a distance, right? It always sounds so mysterious.
Yeah. Right. It's like, two particles on opposite sides of the universe can somehow be linked in a way that, measuring one instantly affects the other.
It's like they're communicating faster than the speed of light, which, Einstein wasn't too happy about.
Yeah. Einstein called it spooky action at a distance. He really didn't like it. He thought there had to be some hidden variables we weren't accounting for, that quantum mechanics must be incomplete.
So is entanglement really breaking the laws of physics then?
Well, that's the thing. It's not. We can't use it to send information faster than light.
Oh, okay.
There's this rule called the no signaling theorem that prevents that.
Right.
So it's weird, but it's not breaking the universe as we understand it.
Okay, that's a relief, I guess.
Yeah.
But if everything can be entangled, and the universe is splitting all the time, creating all these different outcomes, does that mean that probability just goes out the window? Like, if everything that can happen does happen, what's the point of even talking about the odds of something occurring?
That's a great question, and it gets to the heart of how we think about probability in a many-worlds scenario. The traditional way of thinking about probability, like, the odds of flipping a coin and getting heads or tails,
Right.
doesn't quite fit in a universe where, like, every outcome exists somewhere.
So how do we make sense of probability in a many worlds context?
Well, Carroll argues that a Bayesian approach to probability makes more sense here. So Bayesian probability is all about updating our beliefs based on the information we have.
Okay.
So in a many-world scenario, every possible outcome of a measurement, it occurs in some branch of the wave function.
Right.
And probability becomes about our lack of knowledge of which branch we'll end up experiencing.
Okay, so it's not that probability doesn't exist, it's just that our experience of it is kind of filtered through this lens of which branch of the wave function we happen to find ourselves in.
Yeah, exactly. You got it. Now, let's take this idea of a branching wave function and try to connect it to our everyday experience for a second. If everything is this, like, quantum soup of possibilities, how do we get the classical world that we perceive with its seemingly solid objects and clear cause and effect relationships?
Yeah, that's a big leap going from this quantum fuzziness to the concrete reality we see around us.
It is a huge leap, and this is where this idea of emergence comes in.
Emergence.
Right. Carroll suggests that spacetime itself, the very fabric of reality, might actually emerge from the wave function.
Hold on, you're saying space-time emerges from the wave function.
Yeah.
So the very stage on which the universe plays out is built from these quantum connections.
Yeah, pretty much. It sounds crazy, but it kind of makes sense when you think about how entanglement seems to be at the heart of so much of what's strange about quantum mechanics.
Yeah.
It suggests that what we perceive as, a solid objective world is just like one level of reality,
Right.
an emergent property of this much deeper, more interconnected quantum realm.
So the world we experience is almost like an illusion. Not that it's not real, but that it's just like one way of looking at a much more complex reality.
Exactly. It's like how a table seems solid, even though it's mostly empty space at the atomic level. The solidity of the table is an emergent property of how those atoms are arranged and interact.
Okay, I think I'm following.
And in a similar way, seemingly concrete nature of spacetime might emerge from the underlying entanglement structure of the wave function.
Wow. Okay. But if space-time is emergent, what happens to it in extreme situations like, black holes?
Hmm.
It seems like the rules of reality might completely break down in those places.
Black holes, yeah, they're a whole other can of worms. They push our understanding of physics to the limit.
Definitely.
And they might hold some clues to understanding quantum gravity, which is like the holy grail of modern physics.
Yeah, they've always been fascinating, but also kind of terrifying to me.
Yeah.
Tell me more about why there's such a challenge to our understanding of the universe.
Well, first of all, the regions of spacetime where gravity is so strong that nothing, not even light, can escape.
Yeah, the ultimate.
Right. And this leads to a really weird paradox. Because you see, information is supposed to be conserved in the universe, just like energy.
Okay, like the law of conservation of energy.
Exactly. You can't create or destroy energy, you can only change its form.
Right.
But black holes seem to violate this principle.
What do you mean?
Well, when something falls into a black hole, it seems like all the information about that object is lost forever. Poof, gone. This is the black hole information paradox, and it's a huge mystery.
So everything that falls into a black hole, all the information it contains, is just gone. It just disappears.
That's what it seems like, which is a big problem because it contradicts what we know about how the universe works.
Yeah, definitely a problem. So is there any way to resolve this paradox?
Well, one idea is that black holes actually have a huge number of internal states, even though they appear, featureless from the outside.
Okay.
This would mean they have entropy, which is a measure of disorder or randomness.
So black holes aren't just empty voids. They have some kind of internal structure.
Yeah, that's what the math seems to suggest.
Wow. This is all getting very complex.
I know, right? We're talking about parallel universes, black holes that might not actually be black, and the very fabric of reality being, like, woven from entanglement.
My head is spinning.
Mine too, to be honest. But it's exciting stuff, right?
Yeah, it's mind-blowing, but definitely exciting. There's so much we still don't know about the universe, and it seems like every new discovery just raises more questions than it answers.
Absolutely. And something deeply hidden really makes you think about the universe in a whole new way.
Definitely. Well, folks, we've covered a lot of ground today. We've talked about the many worlds interpretation, entanglement, emergent space-time, and the mysteries of black holes.
We've barely scratched the surface, really.
I know, right? It feels like we've only just begun to explore the depths of this quantum rabbit hole.
There's always more to learn.
Exactly. But unfortunately, we're out of time for today. But don't worry, this isn't the end of our journey. We'll be back soon to continue our deep dive into something deeply hidden and explore even more mind-bending ideas about the nature of reality.
So stay tuned.
And keep those brains firing. Until next time, folks.
All right, so we're back. And I gotta say, I'm still reeling from all this talk about, like branching universes and black holes that eat information.
Yeah, it's heavy stuff, for sure. But I'm curious, if this many worlds interpretation, if it's as elegant and potentially unifying as Carroll suggests, why isn't it more widely accepted? Like, it seems like there's still a lot of resistance to it in the physics community.
Right, like why are so many physicists hesitant to embrace the idea?
Well, I think part of it is, like, historically, physicists haven't really wanted to delve too deep into the philosophical implications of quantum mechanics. There was this whole, like, shut up and calculate mentality. Just focus on the equations, make predictions, and don't worry too much about what it all means. But Carroll's saying that, like, understanding the foundations of quantum mechanics is crucial if we want to make progress on these big questions, like, unifying quantum mechanics and general relativity.
Exactly. And thankfully, more and more physicists are starting to come around to that view. But, there are still some conceptual hurdles that make many worlds a tough pill to swallow for some people.
Like what? What are the main criticisms?
Well, a common one is that, this whole idea of infinite universes branching off every time there's a quantum measurement, it just seems too extravagant, too outlandish. Some physicists argue that it's like an unnecessarily complex explanation.
I can see that. It definitely challenges our everyday intuition about how reality works. But then Carroll argues that it's actually the simplest interpretation, right? The one that takes the math at face value without adding all this extra stuff.
Right. When you start trying to, get rid of the many worlds, like with those collapse models or hidden variables, you often end up making the theory more complicated.
Okay, that makes sense. So, but even if we accept this idea of many worlds, are there any practical implications? Like, does it change how we should live our lives?
Well, that's a question that Carroll actually explores in the book, and it gets into some really interesting philosophical territory. On a day-to-day level, probably not. We still experience the world as this single branch of the wave function with seemingly random outcomes.
Right.
But it does shift our perspective on things like choice and responsibility.
Oh, no, so.
Well, think about it. If every decision we make leads to a branching of the wave function, that means there's a version of us out there who made every possible choice.
Yeah.
It really makes you wonder about free will and like whether our choices actually matter on this grand cosmic scale.
That's a bit of an existential crisis waiting to happen.
It is. But Carol argues that we shouldn't get too hung up on this idea of like our future self in a many worlds universe.
Okay. I mean, I can see why that might be tempting, but
Yeah.
why not?
Well, because each branch represents a distinct person. It's like, identical twins. They're separate individuals, even though they share a common origin.
Right.
So it's not like there's one true you out there who made all the best choices, just a multitude of individuals experiencing all the possibilities.
Okay, that's kind of comforting in a weird way.
Hmm.
But what about the ethical implications? Like, if there are infinite copies of us experiencing all sorts of outcomes, good and bad, does that change how we think about morality?
That's a great question. And honestly, it's one that philosophers are still grappling with. But Carroll does explore some thought experiments where, the difference between a many worlds view and a single world view could potentially lead to different moral choices.
Can you give me an example?
Sure. Imagine there's a quantum experiment, right? And it has two equally likely outcomes. One is like amazingly good for humanity, and the other is, just slightly good. In a single worldview, it seems like a no-brainer to do the experiment, right? Either outcome improves things.
Yeah, you're guaranteed a positive outcome.
Right. But in many worlds, you're guaranteed to create a branch where that less good outcome happens. So even though the good outweighs the bad overall, you're also creating, suffering in some branches. And that raises questions about whether we should consider the well-being of those in other branches, even if we can't, interact with them.
That's a lot to consider. I'm gonna have to think about that one for a while. But overall, I gotta say, as strange as this many worlds interpretation is, it's also incredibly exciting. Like, it just opens up so many possibilities for understanding the universe in this much deeper way.
Totally. And something deeply hidden, it doesn't give us all the answers, but it's such a powerful and thought-provoking starting point for anyone who's, brave enough to really dive deep into this quantum rabbit hole. It challenges us to consider a universe where everything is quantum, even space-time itself.
Right. And that the world we experience, with our familiar objects and our seemingly separate events might just be this emergent illusion, just a convenient way of talking about this much stranger and more interconnected reality.
Exactly. I think one of the biggest takeaways from the book is that it encourages us to really question our assumptions about, what reality actually is.
Yeah. To embrace the mystery of it all, to remember that science is a journey of ongoing discovery.
Absolutely.
That there's still so much we don't know, but that's what makes it so exciting, right? So to all our listeners out there, keep questioning, keep exploring, and keep diving deep into those wonders of the cosmos.
And that's a wrap for today's episode of Bookercast. We hope you enjoyed diving into it as much as we did. Thank you so much for spending your time with us. Your support means the world, and we can't wait to hear your thoughts on this episode.
Don't forget to subscribe, hit that like button, and share this episode with your fellow book lovers. And let us know your thoughts in the comments below. We love hearing from you. See you in the next deep dive. Bye for now, and happy reading.